Steady state exercise is when the body is working at a steady state, meaning lactic acid removal occurs at the same pace as lactic acid production. To put a clear, effective visual of steady state in your mind, an example of this is consistent running. Heart rate. Prior to exercise, the heart usually beats between 60 and 80 beats per minute in untrained men and women, but this rate is generally much lower in trained athletes. Stroke volume. Stroke volume increases to its highest level during submaximal exercise and does not increase further during maximal exercise. Stroke volume actually achieves its maximum amount at between 40 and 50% of the VO2 maximum. In trained athletes, this generally means 120 to 140 beats per minute. The greatest increase in stroke volume occurs in the transition from rest to moderate exercise. During maximal exercise, stroke volume does not increase from its peak at 120 to 140 beats per minute, as the left ventricle is, at this point, already full of capacity. The body tolerates maximal activity for as long as it can, but by simply increasing heart rate and maintaining stroke volume, although eventually the body will fatigue if the demands of the maximal exercise are too great. On average, the cardiac output is around 5 litres per minute. When blood is circulated around the body, various organs receive more blood than others. However, whilst exercising, the muscles need more blood in order to supply them with energy. The blood flow is redirected to the body. This is done by constricting the blood vessels that lead to the organs that don't require a large blood flow. Also, dilating the blood vessels feeding to the muscles that do. Vasoconstriction is the process to which the blood vessels constrict, whilst the process of blood vessels dilating is called vasodilation. Thermoregulation. During exercise, core temperature initially increases from resting levels, signaling heat loss responses to achieve a new steady state core temperature. Steady state exercise increases swelling. This beneficial response is because of the significant increase in plasma volume that occurs during steady state exercise. Increased plasma volume supports sweat glands functioning during heat stress and maintains the correct plasma volume for the cardiovascular demands of the exercise. Therefore, a trained person will store less heat early during steady state exercise, reaching a thermal steady state sooner and at a lower core temperature than an untrained person. The training advantage for thermoregulation occurs if the individual fully hydrates during exercise. Blood pressure. During steady state exercise, dilation of the blood vessels in the active muscles increase the vascular area for blood flow. The alternate rhythmical contraction and relaxation of the skeletal muscles forces blood through the vessels and return it to the heart. The oxygen dissociation curve is a graph that shows the relationship between the percentage of oxygen saturation of blood and the partial pressure of oxygen. During steady state exercise, increased temperature and lower blood pH concentration affect the oxygen hemoglobin dissociation curve in such a way that more oxygen can be unloaded to supply the active muscle. In prolonged high-intensity exercise, large amounts of lactate enter the blood from active muscles. At exhaustion, blood pH can approach 6.8. Only after exercise ceases does blood pH stabilize and return to 7.4. The majority of oxygen is transported in the blood by hemoglobin, to which it reacts with hemoglobin to make oxyhemoglobin. The reaction of oxygen with hemoglobin is temporary and completely reversible. This means that oxygen can be unloaded from hemoglobin. Oxygen combines with hemoglobin in oxygen-rich saturation such as the lungs and is released by hemoglobin in places where there is little oxygen, such as working muscles. The S-shaped curve represents the ease with which hemoglobin releases oxygen when it is exposed to tissues of different concentrations of oxygen. The curve starts with a steep rise because hemoglobin has a high affinity for oxygen. This means that when there is a small rise in the partial pressure of oxygen, hemoglobin picks up the binds oxygen too easily. Tidal volume and breathing rate. Increases in breathing rate maintain alveolar ventilation during steady state exercise. During steady state exercise, trained athletes achieve the required alveolar ventilation by increasing tidal volume and only minimally increasing breathing rate. With deeper breathing, alveolar ventilation usually increases from 70% of minute ventilation at rest to over 85% of total ventilation in exercise. This increase occurs because deeper breathing causes a greater percentage of the incoming tidal volume to enter the alveoli. Changes in blood carbon dioxide level and hydrogen concentration cause shifts in the oxygen dissociation curve. These shifts enhance oxygen release in the tissue and increase oxygen uptake in the lungs. This is known as the Burrow effect, named after the Danish psychologist. During exercise, the blood becomes more acidic because of the increased production of the carbon dioxide. Aerobic glycolysis involves the breakdown of glycogen in the absence of oxygen with the formation of ATP plus lactate. The accumulation of lactate terminates the use of this energy system after 40 to 60 seconds of maximum effort. Consequently, it is the system called upon by athletes whose sport demand high energy expenditure for up to 60 seconds, such as 400 meters runners, and those in compound sprint sports such as squash, football, or rugby. Mitochondria. Mitochondria are the site of aerobic respiration. Pyruvate oxidation and the Krebs cycle take place in the matrix of the mitochondria, while the electron transport chain takes place in the inner membrane itself. The Krebs cycle is a series of aerobic chemical reactions occurring in the matrix in mitochondria. The main purpose of the Krebs cycle is to provide a continuous supply of electrons to feed the electron transport chain. This cycle begins with citric acid. Citric acid is a 6-carbon compound and is gradually converted back to the 4-carbon compound, ready to start the cycle once more. The carbons removed are released as CO2. The hydrogens which are removed join with NAD to form NADH2.